Good evening, and welcome to the Scientific Adventures of Beardman. Today I want to start by looking at a guy named Aristotle, who was a genius. He wrote about nearly everything that there is to think about and imagine and wonder about how our world works, which of course is the study of physics. And one of the things he said that the natural state of an object was to be at rest. Now, I am simplifying if you're an expert in Aristotle, but for the rest of us, the natural state of an object is to be at rest. And in order for that to change, there has to be some sort of what he called a violent force. Let me give you an example. You're rearranging your room. You want to move the couch from one side of the room to the other. You exert a violent force, and the couch moves. As soon as you stop exerting a violent force, it returns to its natural state, which is to be at rest. We can see that happen all over the world. You kick a soccer ball. I am off to coach my son's soccer team in a moment. So you kick a soccer ball, that's a violent force. That object leaves its position of rest, and if you let it go, it'll slow down and stop and return to its natural state. Now, of course, it turns out that Aristotle was wrong. That's not what's going on. Well, Newton later came up with what he would call his first, or what I guess we would call Newton's first law of motion, which states that an object will continue to have the same velocity unless the object experiences a net external force. A couple things about that last phrase there, net external force. First of all, I don't think the term external is necessary. If it is a net force, it will be external. Anyways, the other issue that we will not get into in this video is what net force means. We'll just treat it as though it's a force. And then in a later video, we'll talk about what it means to have a net force on the object. Okay, so let's get to the nitty-gritty of Newton's first law here. An object will continue to have the same velocity unless there's a force on it. Okay? So what he's saying is that that couch will keep moving, but that's not what we see. So, well, what could be going on? Well, many of you know there is a force on the couch. After we let go, there's still a force on the couch. Take a moment, pause the video, see if you can think about what it is before I reveal that in just a moment. Okay? So, what you hopefully were thinking is that, wait, there's friction. We understand the force of friction now, and so there's a frictional force that's bringing that couch to a stop. So it's not that there was no force, and that's why it came to a stop, but because there was a force, it came to a stop. Let's think about some examples where there are no forces, or the forces are very small and we can essentially ignore them. An air hockey table is a good example. If you've ever played air hockey, you know that as you hit the puck, that puck just glides across the table. Imagine hitting it kind of slowly. It just kind of glides across the table. Assuming the table is properly balanced, it'll just keep going until it hits the other side. We can see that that object remains with the same velocity until another force acts on it, and that would normally be the edge of the table. Okay? Another place where we see that much more obviously is when we see astronauts in space, floating around when we'll just say weightless for now. As they squeeze a juice box, the little droplets of water just keep floating until they hit something. Okay, and then wow, then when there's a force, they come to a stop. Now, most things that we deal with experience that frictional force, which is why Aristotle came to his conclusions, which are totally reasonable, until we realize that there's a force of friction. Now, we will discuss force of friction in more detail later on in another video. But for now, just two things are rubbing against each other, they tend to cause each other to come to a stop. I realize I've gone through most of this video without actually defining force. Force, for now, we'll use the definition in most textbooks, which is a push or a pull. Okay, pretty straightforward. You can see why I might have used that without defining it. So anything that's being pushed or pulled would be a force. Okay, so an object will continue with the same velocity unless there's a force on it. Now, keep in mind, that explained the couch starting to move as well. The object was stationary, there was no net force on it. We put a net force on it, that allowed its velocity to change from 0 to some larger value. Now, keep in mind, velocity includes both magnitude and direction. That means that if we change direction, we're changing the velocity, which means there has to be a force in order to do that. Now, the tendency of an object to maintain its current velocity is a property called inertia. So when we talk about the inertia of an object, we might talk about the inertia of a football player. Okay? That is, he's running to tackle the running back. He runs in and he's got inertia. In other words, the natural state will be that object, his body, will continue with that velocity until there's a force. And so there has to be a force to stop him. Okay? So one of the things that we know about a football player is the bigger he is, the harder he is to tackle. Well, Bill Nye perhaps said it best.
Inertia is a property of matter.
Part of one of the taglines of his introduction to his famous TV show. So inertia is a property of matter. Well, if it's a property of matter, how do we measure it? How do we measure inertia? Well, it turns out that mass, measured in kilograms in the SI system, is a measurement of inertia. So when you tell me the mass of something, you're really telling me its tendency to maintain its current velocity. So let's review. Turns out Aristotle was wrong. Newton tells us that an object will continue with its same velocity, whether that velocity is 0 or some other value, unless there's a force on it. Thank you. It's been fun learning with you. See you later on Scientific Adventures of Beardman.